showing that even disorder can generate patterns. Building is essential to the expression of humanity. In our creations, we strive beyond pure function toward commentary and celebration. When we set out to create, the patterns and mathematics and nature guide us in our designs. It's hard to overlook the parallels between natural and man-made forms. But there is more to our creations than mere imitation. Man has also calculated nature's proportions. Ancient thinkers looked at nature and wondered if they could duplicate the gods' designs. They came up with the golden section, the measurement of the gods. Take a segment and divide it so that the ratio of the smaller segment to the larger segment equals the ratio of the larger segment to the whole. The numerical value of this proportion is 1 to 1.618. If you construct a rectangle based on this measurement, you can see the ratio is roughly 8 to 5 or 5 to 3. The same numbers found in the Fibonacci sequence. The ancients believed these numbers were sacred, and that might have been because the same proportions can be found in nature. For centuries, artists and architects have built these mystical numbers into their structures.
In the times before the modern age, people gave value to the numbers that buildings are made out of. For example, something might be 3 feet wide and 5 feet high. And those numbers had meaning. The number 3 symbolized God in nature, for example. It also symbolized the Holy Trinity. It had a real symbolic meaning. And the number 5 symbolized humanity. And you'd get the two and you'd put them together and you'd have a shape called the golden section.
Many of our greatest structures and works of art subscribe to this proportion. The Parthenon, Notre Dame, even Michelangelo's creation falls within these so-called divine proportions. But few would suggest Michelangelo painted by numbers. He was creating what felt right to him, what he felt was beautiful.
It's built into us to understand the relationships amongst forms, to understand the way patterns relate, and to make shapes that relate to each other, that are harmonious just the way the speech that we make is grammatical and makes sense. And so intuition is going to go for that shape without sitting down and calculating, oh, it's exactly 1 to 1.618.
What of invisible beauty? There are patterns in the air, sound waves that can make our spirits rise. Again we find hidden structure, a mathematics of music that predicts sounds we will like. Legend tells us the Greek philosopher Pythagoras discovered the relationship between numbers and sound while walking by a blacksmith shop.
He heard some hammers falling of different weights. One hammer was 12 pounds, another was 9, another was 8, another was 6. So he noticed that each hammer made a different sound, and when they were struck together, they harmonized. They formed a certain type of interval. So this is the 12 pound, this is the 6.
Some musical math is as simple as x and 2 times x.
So they're both, 6 and twice 6. They sound basically the same sound, but what we call an octave apart.
The relationship is easier to understand when you use strings. If you take a single stretched string and pluck it, it sounds a note. Notes in harmony with this one come when you divide the string at precise points. If you divide it in 2 parts by pressing on the middle, it sounds an octave. In 3 parts, it sounds the 4th. In 4 parts, it sounds the 5th. A discordant sound results when the division of the string does not come at an exact interval. These simple ratios represent the foundation of our musical scale.
And what this meant was that mathematics had a concrete relationship with the world, that the world worked in a mathematical way, and that simultaneously our own sense, our own aesthetic sense, that makes us recognize harmonies and disharmonies, is a way of perceiving that mathematical relationship in the world. And so there's this wonderful threefold connection between a human mind that can experience this, the mathematics themselves, and the physical world.
By the Middle Ages, architects and composers were linking the mathematics of music and the structures they built. One architectural measurement, the golden section, can be translated into an interval called the major sixth. This is the music of the nautilus shell and breeding rabbits. Different measurements correspond to different sounds. Now, listen to the architecture of Notre Dame.
People would go to the cathedrals, and they had a full-time choir, I think it was 60 people in Notre Dame, singing music made up of the intervals that were the same as the intervals, as the proportions that actually composed the building. The buildings were designed literally to embody musical intervals, the musical tones, the musical intervals, say a third or a fifth or a fourth. Those were ratios that were taken from music and transposed literally into buildings.
The relationship between structures and sounds suggests that mathematics are essential to man's creation of beauty. But numbers cannot explain it all.
Now, there's certain basic principles that are going to remain in there. But with something like beauty, you can't legislate that. Because you don't know what it's going to be.
And that's why beauty is going to be something different for every person.
Keep watching. Discussion topics and activity and resources for patterns, symmetry, and beauty are up next on Assignment Discovery. Now that you've seen patterns, symmetry, and beauty, talk about this. Look for examples of the Fibonacci sequence and the golden section in nature. What are some examples of the Fibonacci sequence and the golden section in your immediate environment? How are these relationships expressed? Now try this. Using straws, tape, and a ruler, construct a model that embodies the golden section. For your measurements, use different sets of numbers greater than 3 from the Fibonacci sequence. Log on to DiscoverySchool.com for curriculum materials and resources to support patterns, symmetry, and beauty. To learn more, Assignment Discovery suggests Life by the Numbers by Keith Devlin.